All right, well, let's go ahead and begin. Hope everybody is doing well. Let's go over a couple of announcements here and then dive right in. First of all, I hope by now you've gotten the textbook. Classes started a week ago yesterday, and we had our first lecture a week ago today. So hopefully that's enough time for your book to have been delivered. I think it's a good idea for you to be reading the textbook sections that correspond to what we're covering in the course. And so most of the lectures I'll try and put down at the bottom of our announcement screen which book section goes along with this class lecture. So for instance, today's lecture on economic equivalence means that you should be reading section 1.7 of your textbook. The other thing that's pretty important is printing out paper copies of the in-class exercises, because we're going to be having a lot of those where you'll need to do a sketch or maybe write on top of a cash flow diagram, and just having the paper copy is a lot better than simply having it up on your screen. All right, homework 1 is due on Friday, and you need to submit that to Blackboard before 12 p.m. At 12 p.m., the link will vanish and you'll no longer even see it in the system. And by the way, if you want to have access to the PDF file of the assignment description later on in the semester, then you should save a local copy for yourself. If you haven't already done that, save the PDF of the homework assignment, because once it vanishes, you won't be able to access the assignment description any longer. Now, I've mentioned before that it needs to be a PDF file that you submit, so don't just turn in a series of JPEG images taken off of your camera. Translate it into a single PDF file, and the advantage of doing it that way is that then the grader has the option of annotating right on your paper. And what that means is that the grader can put little notes and help you to find your mistakes when you've made them. And then the other thing to pay special attention to is when you're taking the photo that turns into a PDF, using Cam Scanner or some other app, is it clear? Is it in focus? Is it well lit? Are you avoiding shadows? Put a little bit of effort into making sure that it's a good image quality. And one way to ensure that it turns out clear and has great contrast is if it's a black and white PDF file. And so please submit your assignments as black and white. All right, any questions related to these announcements before we continue?
Yeah. The textbook, my brother actually took the class a couple semesters ago, and he has the 7th edition of instead of the 8th. Is that a big deal, or?
Well, since I write the homework assignments, it's not a big deal. Since the concepts are largely the same, and I think most of the chapter ordering is the same, as long as you don't mind occasionally having to find where the material is in the older book, that's fine. The material itself is close enough that I'd say go for it. Use the older book.
Okay, thank you.
All right. Okay, so economic equivalence. By the way, thank you to those of you who have your webcams going. I really do appreciate that. It makes this a more human experience teaching remotely, and if you ask your questions with the microphone, that's another thing I really like. So please feel free to unmute yourself and ask a question if you've got one. I don't mind it at all. I think it's great. Okay, so time value of money. Let's refresh our memory of some of this important terminology. And there are some synonyms here, and different books or different references call some of these things by a different name. And so I want you to know, for example, that when I label a cash flow diagram as P, some other books maybe would label that as PW or PV, meaning present worth or present value. It simply means money at the present, and our frame of reference being the present is now. But if you were going to be planning a project, and let's say that the project will actually begin in 2 years, and it is at that time, 2 years in the future, that you're actually going to start doing your expenditures or your loan is going to be taken out. The first time something money related actually happens, whether it's an inflow or an outflow, then that is what you'd label as time 0. And so the present means the first time there's something money related that occurs. The future worth, also sometimes called the future value, is a single amount sometime not in the present but in the future. And it's different from an annual series or an annual worth or a uniform series, because in the case of an annual series, the amounts are recurring and they're the same amount in consecutive years. And so if you see that there's a certain amount of money that repeats itself year after year and there's no gap in time, then you wouldn't label those as individual future worths. That would simply be labeled as A equals an annual series of a constant amount. Okay. I thought I heard a question come through, but I don't see it in the chat box. And so if you do have a question, send it again or unmute and ask me. But I thought I heard the indicator, but I don't see anything there. Okay, so economic equivalence is relating a couple of ideas. The idea of interest rates, or depending on your perspective, if you're the person who's doing the loan, then you can think of it as a rate of return because you're getting a profit on the investment that you've made. The other concept that's tied together with economic equivalence, the time value of money, is that idea that because prices are constantly going up, $1 now is inherently more valuable than $1 in the future. So different amounts of money, different numerical values can be economically equivalent. So just as an illustration, let's say $100 now could be economic equivalent to 110 in the future, in 1 year, if the interest rate is 10%. And so I'm not saying that 100 equals 110. Those two numbers, those amounts are different amounts, but what the equivalence is an economic equivalence, where the time value of those different amounts has been taken into account. And so, like if we looked at it as an equation, we're saying 110 equals 100 if the 100 is being multiplied by the interest rate and the number of years over which that interest is compounding. So here, 1 plus I to the n power. I've put these amounts into the formula that gives us F equals P times 1 plus I to the n power. And so this is an economic equivalence. Not the same amounts, but the same value. And this works simply by moving the time of money, means that the amounts is also adjusted. And sometimes when we have a graphical cash flow diagram, we will be kind of visually be moving amounts from the future to the present, or from the present to the future, so that we can compare alternatives. You may sometimes have one alternative that occurs over 3 years and a different alternative that occurs over 5 years. And to compare different amounts, we have to combine them into the same time frame. And so there's going to be a process that we'll start with today, where you can see here in this description I'm saying you move money. Moving money means you're changing the time and therefore finding the economically equivalent amount. So it's not going to be an equal amount in the future or in the past, but it will be economically equivalent because you're going to take the interest into account. All right, now here are the labels that we've looked at before. And an economic equivalence of, for example, 100 at the present, the same amount that we were talking about before, where if you have an interest rate of 10% per year, if you made a deposit of 100 now, then that means that you could withdraw from an account the amount of 110. Now, these are economically equivalent in terms of the magnitude of the amounts. I'm not saying that a deposit is the same thing as a withdrawal. You'll sometimes have problems where it's going to ask you, if you make a deposit, how much can you take out in the future? And then those would be different directions in a cash flow diagram, because one is a deposit, one is a withdrawal. There may be other problems where it says you're going to save a certain amount of money in the future, and so then you want to know how much is that future savings worth in today's terms. And if that was the type of problem you're solving, you wouldn't change the sign or the direction of the cash flow arrow. You would just move it back in time. And so you kind of have to look at the context of the problem to know whether you're going to be flipping the direction from an inflow to an outflow, or whether it stays the same. So in this diagram, what we're saying is that 100 now is economically equivalent to 110 withdrawn in a year if it's invested at 10%. Okay, so hopefully this makes sense. Anybody have questions so far regarding this discussion of equivalence? All right. Now, there is a common mistake that I see sometimes students will make, and that is the finding the previous amount. And we looked at this in one of our earlier in-class exercise, that one that was both a currency exchange and you were finding out how much was deposited originally. Okay, so consider this hypothetical that you can receive $100 in 1 year or a certain amount today. And if the interest rate is 10%, how much should you receive today? The mistake that sometimes people make is just thinking that 10% of 100 is $10, so it must be $90 that you should receive today. But that's not actually correct. Remember that if you set this problem up, the cash flow diagram looks like this. You're getting 100 in the future. The present for today is unknown. The interest rate is 10%. And the formula that we use to solve problems like this, you've seen before, the future amount is the present amount times 1 plus I to the n power. And so you need to solve for P, which means that you have F divided by 1 plus I to the n power. So if we do that and solve for P, you'll see that it's $90.91. So if it had been the $90, the today amount, compounding in 1 year, that would have only given you $99. And so it needs to be more than $90 in today's terms for it to be that nice round number of 100 1 year in the future. So when you get problems like this, my recommendation is maybe above the text, identify the variables. So for example, on the paper you could write F above 100, and then that would be in your mind an indicator that that's talking about a future amount. And then you could write N above the number 1, and then that would tell you that your number of compounding periods is 10%. And then they've already kind of identified the I for you, but what you could do is you could write I equals 0.1 as a reminder that you need to convert from percentage into the decimal equivalent. So that's just one tip. In a problem statement, write the variables next to the applicable text. Okay. Cash flow diagrams are a really quick and easy way of summarizing a problem. And what's shown so far on the screen is find the future equivalent of $11,000 now. And so if you deposit $11,000 at the present, how much could you withdraw 3 years in the future? And so we know that the unknown is the F, both because of the question marks and also because it's the dashed line. And so we can summarize this problem type as a find F given P. Or even more simply than that, we can just say F slash P. And so it can be, quite obviously here, numerator and denominator. Sometimes it may be expressed where it's not quite as clear, like in this problem it's P slash F, but it's still meant to be one of them is the numerator and one of them is the denominator, because we're going to look up ratios out of the back of the book, and they're numbers that you can multiply by this ratio to find the unknown. So part of the reason why we have a convention for how to summarize problems like this in language is because of the way that the tables are set up for later. So let me just be more clear about what I'm saying. You could call this given P find F, I mean, those just rearranging the order of this sentence. You could say given P, find F. But the reason why we say find F given P is that then in our minds, that helps us to think that F is the numerator, P is the denominator, and when we look up in the back of the book these tables, let me get the book and I'll show you what I mean. Okay, so here in the back of the book in the appendix is just page after page of factor tables. The 0.5% interest, 0.75% interest, 1% interest, and then there's different columns, and these columns, let me hold it up to the screen there, the columns have titles on them. The titles are like F/P and P/F, A/P, and so on and so forth. And so we have to get in the habit of standardizing the way that we translate a cash flow diagram into this symbology that's at the very bottom, because it's this symbology at the very bottom that we'll use for problem solving. So when you see a cash flow diagram like this, what you should write down is find P given F. So this is a P/F problem. Okay, now what about this one? Find A given P. So then that makes this an A/P problem. And what it means in practical terms, is if you deposit $7,500 today into some account that's earning interest, presumably, how much could you withdraw each year for 3 years, and then with that last withdrawal, the account balance would be down to 0. That's what this kind of a problem is asking, is what's the economic equivalence of a lump sum today? And that's called an annuity. If any of you are kind of into finance or investing, that sort of thing, maybe you've heard about annuities before. It's maybe something that old people tend to think more about than younger people, but you know, when you're getting close to retirement, you want to have a guaranteed source of income over the entirety of your life. And so you can purchase an annuity by giving a lump sum to an investment company, and then they promise to pay you a certain fixed amount every month for a certain number of years, or sometimes for the remainder of your life. And so that's what this is. This kind of problem is find the equivalent annual amount, so it would be the same amount every year for 3 years that's economically equivalent to the lump sum. And so that last withdrawal that you're getting would then finalize the value that had been deposited at the present. Okay, now what about this one? Think, what's the unknown? What's the given? So this is find P given A. So this is a P/A problem. And so if you wanted to find out what is the value of P, then for a certain interest rate, for a certain number of years, so here it looks like n equals 3, we could go to the table that I just held up in the appendix. We could go to the applicable interest rate table, and we can find where is the column that says P/A, the present worth column, and we'd go down to n equals 3, and then we'd find out what's the factor. And I'm just right now looking at the 3% table, and the 3% factor is 2.8286. And so what that means is that the present value P would be 2.8286 times the magnitude of the amount. So 12,500 times that factor that I just mentioned, and then that's just a really quick and easy way to solve for P. We'll do that. We'll do that in coming lectures. Not today, but what I wanted to introduce you to is this notion of a standardized way to translate the visual cash flow diagram into a ratio. Interject if you've got any questions. All right. Let's take a look at in-class exercise number 4. Hopefully you've got it printed. we're going to work the first two problems together, and then I will put you in breakout groups for problems 3 and 4. All right. Okay, so the first problem here, the owner of a construction company is thinking of buying a new cement mixing plant. It's projected to cost $550,000. If she buys it, then the extra revenue will be $85,000 for each of 6 years. Okay, so the language there is telling you that it's going to be an equal amount, the same amount consecutively. And so this language is defining an annual series where it's saying the extra revenue will be $85,000 for each of 6 years. So that's saying A equals $85,000. And the 6 years that it's talking about is presumed to be the 6 years that immediately follow the purchase of the equipment. So we're not talking about 6 years, many, many years in the future. It's like you make the purchase at 0, and then immediately after the purchase, the revenue begins, and it's paid out at the end of the first year. So that's the end of period assumption. Okay, the problem statement says, then the machinery will be sold as scrap for $50,000 at the end of the 6th year. Draw a cash flow diagram from the company perspective, including labels. All right, so I'm going to pause for a moment, and I'd like you to take a crack at translating this statement into a cash flow diagram. And then in just a moment, I'll bring up the solution on the screen, and we'll talk through together all of the elements that should be in that cash flow diagram. All right. Well, hopefully you've got some idea of what the cash flow diagram should look like for this one. Let me pull up the key and drag it onto the screen here. All right, there we go. All right, so a lump sum outflow of $550,000 now means that the arrow should be going downward from our horizontal axis, and you need to label each of these periods. They're annual periods here, and so it's at time equals 0 that you've got an arrow down. That's a relatively large arrow because $550,000 is a lot. P equals 550. So we're putting the units, which are dollars, the P for the present value, that's the lump sum outflow. And then it's the extra revenue of $85,000. And so you'll know that these arrows are roughly the same length. You know, this one maybe looks like it's a little bit shorter, but this is just a conceptual, not to scale sketch of the problem, so we don't have to sweat too much if it's a fraction of a millimeter shorter. But you'll notice here that A equals 85,000 is our indicator that the amounts are the same through each of the 6 years. Now, maybe what some of you did was combined that last arrow in year 6. My past experience tells me that maybe about half the class would have made this so that it says F equals, and what's the combined amount there? Is it 135,000 at year 6? So some of you would have said that what we have is a 5-year annual series and then a combined lump sum amount, and that's fine. You know, that's not correct. Excuse me, that's not incorrect. It's just my personal habit is to leave the annual series discrete, and then what you can do is just draw the arrow distinctly on top of that. And so what this clearly conveys is that the components that contribute to F is in part, there's the annual series part of it here at 6, and then there's lump sum amount as well. Somebody asked, what about having the recurring series starting at time 0? And no, that would not be correct. And the reason why is our default assumption is the end of period assumption. And so our default assumption is you're getting revenue for using the cement plant. And so you don't get the revenue at the beginning of the year, you get the revenue at the end of the year. So it would count it as a mistake if you had the 85,000 starting at time 0. So would it be wrong in a test if we done the 5-year annual and the 6th at 135? No, that wouldn't be wrong on the test. As long as you had clearly labeled everything and the amounts are correct, then you would not be penalized. It's just, I think for some reasons that you'll see later on when we move amounts from place to place, I think it makes sense to keep it separate. But if you combined it, I wouldn't deduct points. Okay, so are there other questions about problem number 1? Okay, problem 2. You want to receive 95,000 next year from an investment account that offers 9% annual interest. So draw the cash flow diagram and calculate how much you should deposit today. So this is real similar to one of the examples we've already looked at today. So let me give you a moment to represent this situation as a sketch and do the calculation. When you've got the answer, type it into the chat box, your guess for what is the present amount that you need to deposit. Let's take a quick look at the solution here. Okay. All right, so you want 95,000. So what it looks like is in 1 year you're taking a withdrawal. We've got a solid arrow there because we know the amount is 95,000. Just somewhere near the cash flow diagram, it doesn't matter if it's above or below or to the left, just in the proximity of the cash flow diagram we should identify what is the interest rate. And then here we have this dashed line and P equals unknown question mark to illustrate that that's what we're calculating. So with this given formula that relates future value and present amount, we can rearrange it to solve for P, and as everybody indicated in the chat window, 87,155 and 96 cents. Okay, now a quick word about rounding off. When you use a formula like this, you can be accurate to the nearest penny. You don't need to be accurate to more precision than a penny, so you don't need to keep track of like tenths of a penny. You can just report the answer to the nearest penny, but don't round it off to the nearest dollar. Later on, when we start using the factor tables in the book, those won't allow you always to be accurate to the nearest penny, because sometimes those factor tables have decimals that are only like four decimal points, significant figures. So like if we had used a factor table that had 4 significant figures, we'd have to round off to 1, 2, 3, 4 to the nearest $10. So later on we'll be rounding off, but for now it looks like everybody did this. In the chat window they were reporting it to the nearest penny, and that's great. Okay, I'm going to put you into breakout groups now, and I had a former student suggest to me that the magic number for a breakout groups is 5 students. She said that if it's less than 5 it's too small, and if it's more than 5 it's too big. So I'm going to try the magic number. I'm going to put you into breakout groups of 5, and what I'd like you to collaborate with is this problem 3 and problem 4. Now hopefully you've got it printed, because when I put you in the breakout room you're not going to be able to see my screen any longer. If you don't have it printed, you could just do a quick screenshot right now by pressing the print screen button while I have the problem up on the screen. So this is problem 3 and problem 4. Okay, so problem 4 is about moving the money from year to year, and what you're going to need to do in problem 4 is this amount that is here in year 1, so it's 12,500 equal amounts. We need to move it all to year 4, and so this amount that's in year 1 needs to move 1, 2, 3 years into the future. And you're going to use this formula to do it. So you're going to find out that single amount that's in year 1, what is its equivalent if you move it, if it compounds and therefore increases in amount to year 4. So it's going to be a single amount that moves 1, 2, 3 years in the future. And then you'd move this amount, that's here at year 2, you'd move it 1, 2 years in the future. And then this amount that's at year 3, you'd compound that 1 year to the future, and then you have the amount that's already at year 4. It doesn't need to move at all, so it doesn't need to be compounded with that formula. And then the combining of all 3 of these other arrows with the one that's already at year 4 is how you find the magnitude at year 4. And so this process that I'm talking you through, you are going to apply F equals P times 1 plus I to the n power. And then there's this other approach. It looks slightly different on your page. If you've printed out the in-class exercises, the formula that's on your page isn't as obvious that what you're looking at is a ratio. So another way to calculate F is F equals A times the right-hand side of this equation. So try it out the other way. So I'm putting it into the group so you can talk through the process together. Let me begin that now. Breakout groups. Let me try and go for whatever we need. All right. A YouTube recording so that this is on there. All right, so in problem 3, is it better to store the fuel after buying it now, or is it better to buy it in the future at the higher price? So here's the way that I analyzed it. If you buy it now, then you would have to pay the $2.20 a liter times 100,000. So this is the purchase price of the fuel, and then this is 3 annual payments for the storage fee. So the total number of dollars you're going to spend is $260,000. And so if you're going to set all of that money aside now so that it's available to do this scheme, you need $260K. The alternative is to invest this. And so let's say you take the $260 and you put it into an account that's making 7%, then the number of dollars you'll have available after 3 years is now $318,000. So this is now the money you have available, and the cost of the fuel would only be $265, which means you're going to have leftover money. And the fact that you have leftover money is the indicator that it's better to invest the money and then buy the fuel at the higher price rather than to store it. Okay, so hopefully you got the same idea that it's better to invest the money and buy it at the higher price, and you need to have some sort of supporting rationale for that. Mine was just to look at, if you invest the lump sum, how much would you have in the future? All right, now problem 4. What I did was I gave each one of these arrows a label. And so I'm saying, for example, to get this arrow A to year 4, it's going to have to be moved 3 years. And so it moves 1, 2, 3. To get it from 1 to 4, there are 3 years that it compounds forward in time. So if it's compounding, that means the amount is getting larger. And so 12,500 compounded for 3 years at 5% per year means that that value in year 4 is going to be 14,470. And then arrow B, which is the same 12,500, but now in year 2, it only needs to be compounded forward 2 years in time. So we find the amount for that particular arrow once it's been moved from 2 to time 4. And you got to do the same thing with this arrow C to move it 1 year forward in time. And now arrow D is already at time 4, so we don't have to do any compounding for that. But the sum of those amounts is 53,876. So that's one approach where we take each one of these amounts as an individual present value and we compound it to the future. The other way to handle it is with that formula that I showed you at the beginning of the example. F divided by A is 1 plus I to the n minus 1 divided by I. So we substitute in, rearrange A on the right hand side of the equation and then this factor equation, and so we get the same 53,876. All right, it's 12:50. I said I was going to let you go a minute or two early today and I failed. I'm really compounding the time that I owe you back. Hopefully I'll be able to repay you your time on Friday. But if you have any questions about the homework or about today's in-class exercise, feel free to send me an email. Of course, remember, these recordings are posted on YouTube, so if you didn't have enough time to copy down the solution for a particular in-class exercise, you can find it online. Have a good day, everybody, and I will see you on Friday.
Have a good one.
Thanks, you too.